Hello, everyone, and welcome to today's webinar hosted by Mirus International. Founded in 1991, Mirus has been a supplier of specialized power quality products to reduce or eliminate harmonic problems and save energy in electrical power distribution systems worldwide. The topic of today's webinar is reducing generator size and fuel consumption through harmonic mitigation. Before we get started, let's review today's webinar logistics. All attendees are in listen-only mode. Submit written questions within the question box on the GoToWebinar console at any time during the webinar, and we'll be answering questions during the Q&A section at the end of the webinar. All questions are anonymous to the audience. Now, I'd like to introduce today's speaker, Tony Hubenards, President and CEO of Mirus International. Tony is a registered professional engineer and an active member of the Global Association Institute of Electrical and Electronics Engineers, and has published and presented numerous technical papers on power quality and harmonics. Prior to joining Mirus in 1996, Tony was Chief Facilities Electrical Engineer at a large IBM manufacturing and software development facility in Toronto, where he gained experience in solving power quality related problems, particularly in the area of harmonics. Other work experience includes being a key team member in the computerization of a large oil refinery with responsibility for power distribution, instrumentation, and communication systems. Now, I'd like to turn it over to Tony.
Thanks very much, Julia, and welcome everyone to our webinar today. As many of you know, Mirus has been providing very effective harmonic mitigation solutions since our inception in 1991. We've always known that by eliminating harmonic losses, substantial energy savings could be realized, but it has not always been easy to quantify these savings. I'm so pleased to be able to share with you today an application we've done where energy savings in the form of generator fuel consumption reduction was easily quantified and resulted in a 1.5-month payback on the harmonic filter. So let's look at what we're going to discuss today. I'm going to provide a little background on the case study. Then we'll talk a bit about generators and how harmonics affect generators' operations. We'll talk about nonlinear loads such as variable speed drives, the harmonics a variable speed drive generates, and then how source impedance can affect both current and voltage distortion levels. Then we'll introduce the concept of right size in the generator under nonlinear loading. We'll talk about what the generator manufacturers recommend and what can be done to minimize the effect of that. Then we'll look at various forms of harmonic mitigations for variable speed drives. And then we'll get into detail on the case study. And the case study is a 200 horsepower islanded oil pumping application. We'll review the computer simulations that were done, measurements, field measurements that were compared to those simulations, and then the fuel and emissions calculations that demonstrated the savings. So the project in question was an unmanned islanded oil pumping application on a pipeline near Cotulla, Texas. It's a 200 horsepower 40 volt pump that was supplied by a variable speed drive, and initially they had installed a 176 kilowatt diesel generator. There was no utility connection on this site. So they initially sized the generator basically 1-to-1 to the kilowatt ratings of the pump. The variable speed drive was equipped with an AC line reactor in an attempt to reduce harmonics, but that was not very effective, as it turned out. And after numerous problems, including generator instability and several expensive VFD failures, the generator was increased to a 500 kilowatt unit on the manufacturer's recommendation. Some problems persisted, and therefore harmonic mitigation was considered and eventually applied. With the application of the harmonic filter, there was a payback, as I mentioned earlier, of 1.5 months. So generators, when they're supplied by variable speed drives, will create higher losses in the generator and cause overheating of the generator. The impedance, the higher impedance of the generator will result in higher levels of voltage distortion as the harmonic currents pass through that generator impedance. The high distortion levels can cause excitation control and automatic voltage regulator or AVR issues, resulting in instability of the generator. And the heavier losses will introduce additional fuel consumption, and with that extra fuel consumption are added emissions into the environment. And the standard solution recommended by generator manufacturers is to oversize the generator by 2 or 2.5 times the load. So what's wrong with that standard and recommended solution? If we oversize the generator is going to operate at much more lightly loaded conditions. When it runs at lightly loaded conditions, the generator's efficiencies drop dramatically. A generator has optimal efficiencies in around 70% range, 70% loading range. So as we lower that, the efficiencies go down, and with the efficiencies going down, the fuel consumption goes up. As the fuel consumption goes up, as I mentioned earlier, we're going to emit more contaminants into the environment, and that can cause obviously problems with global warming and other issues related to environmental conditions. And we're going to increase our operating costs. Also, if we're doubling or more the size of the generator, of course we're going to have much higher capital costs. And even though the generator, a larger generator, will introduce slightly lower relative impedance to the load, if there's still enough impedance, typically that the resultant current harmonics passing through that impedance is going to still create voltage distortion levels. So harmonic currents substantially increase the losses in the generator, and this is due for many reasons, but partly because the harmonics introduce stray magnetic fields which result in excessive eddy currents in the generator's windings and in the laminations, and those will increase the losses. And also there'll be increased I2R losses due to the skin effect with the higher frequency harmonic currents tending to flow on the outer edges of the conductors. The generator's high source impedance makes it a weak source. As a weak source, it'll introduce much higher levels of voltage distortion. The internal impedance of a generator is typically 4 to 5 times that of an equivalent size transformer's impedance. So if you're loading the generator at the same level with a nonlinear load that you would be loading a transformer, you're going to have 4 to 5 times the level of voltage distortion on the generator. Generators, even when they're supplying a linear load, do not produce a perfectly sinusoidal voltage waveform, but when there's nonlinear loads, the extra distortion is quite high, and there's significant increases in that level. And often an engineer, in an effort to reduce the fault level in an application so that they can maybe go with cheaper circuit breakers or other electrical equipment downstream, may specify a high subtransient reactance generator. However, when we do that, that extra impedance will increase voltage distortion further, making the problem worse. And as we get into high voltage distortions, we get AVR control issues or excitation control issues. AVRs will sense, do their voltage sensing either to respond quickly to a true RMS value or to a fundamental frequency component. They cannot or should not be or respond to any harmonic distortion. So if the distortion levels get high and the AVR does respond to that, it can cause instability issues. And excitation controls will usually take their power from the output of the generator, and if it's badly distorted, it can cause excitation control issues. So certainly the recommendation to oversize to minimize these problems associated with nonlinear load is required when we have these harmonic generating loads. So in our application today, the nonlinear load is a variable speed drive. Many of the applications out there where harmonics are an issue are associated with the variable speed drives. The schematic shown here is a 6-pulse variable speed drive, which has a 3-phase diode rectifier on the input, which takes the AC power, converts it to DC. We might have a DC line reactor in the circuit, capacitors, DC bus capacitors to reduce the ripple on the DC, and then that DC voltage is applied to the inverter section, which is IGBTs, a set of IGBTs, which switch the DC at high speeds to simulate an AC waveform to deliver to the motor, and that simulated AC waveform can be created at varying frequencies, and that's how we would control the speed of the motor. In this application, the harmonics that are present will typically follow this relationship where it's NP plus or minus 1, where N is any integer, P is the pulse number of the rectifier. And then the harmonics that are present are typically inversely proportional to the harmonic numbers. So the higher the harmonic number, normally the lower the magnitude of that harmonic, if it's present. So when we have a 6-pulse rectifier, as shown here, we substitute P equals 6. When N equals 1, we have 6 plus or minus 1, we have 5th and 7th harmonics. When N equals 2, we have 2 times 6 is 12 plus or minus 1, we get 11th and 13th and so on. So the predominant harmonics we're going to see are 5th and 7th, 11th and 13th and so on. And the input current waveform is basically double humped, pulsed current waveform, 2 humps on the positive and 2 humps on the negative side. So when a drive is supplied by source, the actual current that variable speed drive will draw is dependent upon the impedance of that source. When you have a stiff source, which would be a large transformer with low impedance, so we have a relatively low impedance that the drive is being subjected to, that drive is going to draw very sharp pulses of current. And these sharp pulses contain high levels of harmonics. So in this case, it's a 15 horsepower drive, a 6-pulse drive on a stiff source. The total harmonic current distortion is 108%. So it's got a high level of current distortion. But it's being fed by a stiff source, and therefore with low impedance, and therefore the voltage distortion that this current harmonics passing through the impedance creates is relatively low. So we only have 2.2%, hardly any distortion in the voltage. But if we take that same drive, that same 15 horsepower drive, and now supply it from a weak source, a generator source, with high subtransient, it's typically high subtransient reactance, then that added impedance is going to lower the current distortion. The drive is going to draw current that's broadened somewhat, so there's not as sharp of pulses, and this current wave shape contains less harmonics. So now we've got current distortion of less than 26%. But at that lower current distortion, we have much higher voltage distortion because of the added impedance of the source. So the voltage is almost 14%. You can see very severe flat topping and other distortions on the voltage, and that's a result of the remaining harmonic currents, even though it's much lower than on a stiff source. Even the 26% of current distortion now creates almost 14% of voltage distortion. So let's now take a second and we'll do one quick poll question. We'll ask each of you to answer the question. The question there, for you is that at what percentage of nonlinear loading do generator manufacturers require 2 to 2.5 times oversizing? The answers are 25%, 50%, 75%, full load, or no idea at all. We'll give you a couple of seconds to answer the poll. Okay, so here's the answers. We've got about 19% that think it's only 25% of nonlinear loading. Another 35% believe it's at 50% nonlinear loading, 10% at 75%, and 13% at full load. And a few of you have no idea. Hopefully by the end of this presentation, you will have some idea. So the actual answer is 25%. So it doesn't take very much nonlinear load for the generator manufacturers to recommend that it be oversized. So this is the traditional rule of thumb in a right-sizing approach for generators. When a VSD represents more than 25% of the total load, they become cause for concern. So this is wording that came straight out of a generator manufacturer's application and installation guide. When the amount is higher, then greater oversizing is required. And 2 to 2.5 times oversizing is typical. And they also go about mentioning that oversizing can be avoided by applying effective harmonic mitigation. If you reduce the current distortion to less than 10%, and that lowers the derating requirement to 1.4 times. So for large nonlinear loads or large quantities of smaller nonlinear loads, harmonic mitigation should always be considered. If we can reduce it to even less than 10% THD, then obviously we can get closer and closer to a 1-to-1 sizing of generator to load. So let's look at a few forms of harmonic mitigation that are available to us today. In the application that we're using for our case study, they did include an AC line reactor. So we can have AC or DC chokes that are used on drives. Typically, they'll reduce the harmonic distortion by about half. And that almost always is not sufficient enough to resolve the problems associated with the harmonics. 3 to 5% are typical impedance levels. If you try to go above 5%, the effect or improvement or reduction is minimal, but you also will introduce additional voltage drop. And drive manufacturers recommend 5% as being the maximum. A 5% impedance line reactor is going to introduce a 5% voltage drop at full load. And so if we introduce more impedance than that, then we start having drive-related issues due to the voltage drop. Many applications will look at multi-pulse drive systems, 12, 18, and so on. Those introduce transformer phase shifting strategies to create harmonic cancellation. One thing to note is that the effectiveness of phase shifting diminishes as we get into higher pulse numbers. That's because the phase shifting is dependent upon the phase angles of the harmonics being similar on each of the different rectifier sections of your multi-pulse drive. And as we get into higher frequency harmonics, the phase angles vary much more, and therefore the cancellation can be minimal in many cases. Also, if you have any voltage imbalance or voltage distortion on the power system, that will dramatically reduce the effectiveness of the multi-pulse system. You can have voltage imbalance of as little as 2%, and the multi-pulse, an 18-pulse drive system can be not much better than a typical 6-pulse drive, because again, the cancellation is dependent upon the phase angles being similar, and as soon as you introduce imbalance, the phase angles change on the harmonics. And also you're introducing additional losses. Transformers can be relatively lossy, so now you've reduced the overall efficiency of your VSD system. Tuned passive filters have been used in the past. They're not that common anymore because of the problems that they've introduced. They typically would need to be tuned to each harmonic that you're targeting. So if you need a fifth harmonic being the most predominant, you'd need a fifth harmonic trap. But if all you do is filter the fifth, you're going to have high levels of seventh, so you'll need a seventh harmonic trap and so on. And it ends up introducing very complex passive filter systems, and these can have high capacitive reactance, which can cause problems with generators. This graph here just shows a typical generator's capacitive or reactive capability curve, and on the left side is the capacitive reactance, and if you're outside of this envelope, the internal envelope, this is where the generator will operate properly. If you're outside of that envelope, you're going to have excitation control problems and problems with the generators. And virtually any tuned passive filter is going to, at light loads, is going to be out on this level, and the generator is going to have problems with that. So we definitely would not recommend a tuned passive filter. There are a lot of active front-end drives out there right now that people are offering for harmonic mitigation. These will have IGBT rectifiers on the front end instead of a simple diode bridge. These can reduce the current harmonics in the lower frequency range, so say up to the 50th harmonic. But they will introduce a band of high frequency harmonics above the 50th, typically in the 50th to the 100th, which is related to the switching frequency of the IGBTs. So if you have IGBTs switching at, say, 4 kilohertz, 4,000 hertz divided by 60 is going to be about the 67th harmonic. So you're going to see a band of harmonics out at the 67th. There is a paper that we've published that you can find on our website that talks a little bit about active front-end drives and talks about the high frequency harmonics they introduce and compares them to the solution with a passive filter and a variable speed drive. These AFIs also introduce higher levels of common mode voltage. Any variable speed drive will introduce common mode voltages, and that's again the result of the switching of the IGBTs. So all variable speed drives have an inverter section that has IGBTs, and that'll introduce common mode. But an active front end has a second IGBT section, which also introduces common mode. So you're going to have often twice the level of common modes, and that can cause motor problems and other issues on the power system. The fact that there's a second inverter section typically will double the losses of the VSD because most of the losses in a variable speed drive is related to the inverter section. So if we're doubling the inverter section, we're going to essentially double the losses. And of course they are an expensive solution. And then the final option here that we'll throw out there is a parallel active filter. These generate and supply nonlinear loads with harmonic currents that are essentially out of phase. They supply the load so that the source doesn't have to supply the harmonic content, thereby reducing the current distortion being drawn. These can also introduce high frequency harmonics as they also have IGBTs in their operation. So you're going to have similar issues that you'd have with an active front-end drive. And if you want to make an active filter effective, you're going to need to have at least a 3% AC line reactor on all the variable speed drives connected to that system. Before we leave the parallel active filters, I just wanted to show you a voltage waveform that was measured at a site that I was at where an active filter had been installed. you can see the high frequency ripple on the voltage. The overall voltage distortion at this site was very low. It was actually less than 1%. But all of that voltage distortion was at this high frequency. And that high frequency voltage was causing a power supply in a tester at the facility to burn up as soon as it was energized, as soon as it was turned on. That power supply was resonating at this ripple frequency and therefore overloading and overheating. The only solution at the site was to turn off the parallel active filter to prevent those failures. So the best solution for treatment of harmonics is a passive wide spectrum harmonic filter, our lineator AUHF. This filter reduces the full spectrum of harmonics generated by a 6-pulse variable speed drive. It has a unique reactor. It's built on a common core. The schematics shown here. We have a blocking reactor on the input, compensating reactor on the output, and then a tuned branch reactor tuned with a capacitor. We've designed it to have very, very low capacitive reactive power to make it compatible with generators. So even at no load conditions, the reactive power of the filter is less than 15% of the rated power of the variable speed drive. So this ensures compatibility with the generator. We're also tuned below the 4th harmonic so that we won't attract harmonics from the power system into the filter. So the predominant harmonics in the power system are 5th and above, and so we're tuned below that so that we do not attract those power features. And we're the highest efficiency of all solutions available for variable speed drive applications. This slide shows typical measurement in our test facility. There's a variable speed drive. You can see the input current to the filter that's supplying the variable speed drive. That current is only 5.12% current distortion. And this spectrum shows measurements all the way up to the 500th. So this particular instrument that we're using will measure up to the 500th harmonic. And you can see the X scale here is only 3%. So none of the harmonics are higher than the 3% level. And you can see this would be 5th, 7th. There's fairly low levels of harmonics, even in those lower levels, but virtually no higher frequency harmonics, which are what you would get with the active solutions. So let's look at our case study. Initially, we had the 200 horsepower pump supplied by a 178 kilowatt generator, and there was a 3% line reactor. So we've used our Solve simulation software to create this simple, very simple one line. So we have our generator here. It's 220 kVA or 178 kilowatts. Subtransient reactance of just under 12%. We could put in cables and cables impedances, but we haven't. This is a very short run, so there's very little influence there. And then there's the VFD. This VFD was equipped with a 3% line reactor. It's 200 horsepower, and it was to get the rated flow of 240 barrels per hour is running around 90% loaded. So we get 24% current distortion, 11.6% voltage distortion. You can see the distortion of the voltage waveform, flat topping, a lot of harmonics. This is a scale of 10%, and there's our input current, the double humped. So when we came to site, they had already installed a 500 kilowatt generator. This first simulation, I'm showing no mitigation. There was an AC line reactor. I'll show that next. But without any line reactor, on a 500 kilowatt generator, we're at 7.6% voltage distortion, 45% current distortion. You can see the voltage is still pretty severely flat topped. A fair bit of distortion, much sharper pulses in the current. When we add the line reactor, current distortion drops, voltage distortion drops as well. Slightly better voltage and current waveforms. When we add the wide spectrum harmonic filter, we can see now our current distortion drops to 6.6%. Voltage distortion is now almost eliminated at 1.7%. Virtually sinusoidal voltage and much more sinusoidal current. So if we look and compare the three simulations, we have on the 500 kilowatt generator, we have no harmonics, 7.6%. When we add the line reactor, voltage distortion drops to 5.4. With the filter, it drops to 1.7. You can see the reason the voltage distortion drops is the current distortion is dropping as we remove the harmonic content. You can see the simulation shows a slight increase in power because there are some additional losses with the added filter. However, in the actual installation, when we measured the power consumed by the pump, when it was delivering the same 240 barrels per hour, that was the flow rate that was targeted by the customer, there was a substantial reduction in the power consumption. So voltage distortion, current distortion, relatively close matches to our simulations, both with the line reactors and with the passive filter. And a substantial reduction in current being drawn because the harmonic content is removed, and a reduction in the power consumption. And we believe that lower reduction in power consumption is that the harmonic filter, by improving the voltage wave shape, restoring the voltage peak, improves the operation of the variable speed drive, and therefore lowers the power that it needs to deliver the work to produce at 240 barrels per hour. We've run into this situation before. I'll give you an example here. This is a skydiving simulator ride where this one was located in Orlando, Florida. And this was our customer wanted to prove to the owner of the skydiving simulator ride that if they replaced their 18-pulse drive solution with their 6-pulse drive and our filter, there would be substantial reduction in the power consumption. So these skydiving simulators are basically they're large fan systems blowing air out, and you step in and you can float on the air, and you can see this is somebody sitting in a skydiving position. You can do various tricks and so on. A lot of fun to participate in that. When they run these, they run them at varying speeds, but the two speeds they typically use are full speed when the instructors or a very skilled skydiver is using the equipment, and they're going to run at 889 RPMs fan speed, and the drive is going to go at full 60 hertz. And on the 18-pulse solution, they were drawing 190 kilowatts. When they reduce the speed to 818 RPMs, the drive required just under 56 hertz, and the power consumption dropped to 152. When we switched to the 6-pulse drive and the lineator, you can see at full speed the power dropped from 190 kilowatts to 183 kilowatts, a substantial reduction with no loss of power output. When we dropped to 818 RPM, instead of requiring 56 hertz, the drive only needed to deliver 55 hertz, to run at 55 hertz. So it's running much lower speed, or a lower speed, and the power consumption is dropped even further. So you not only have the reduction in the losses due to the transformer losses of the 18-pulse system, we also have a reduction due to the lower speed of the variable speed drive. So at full load, full speed, there was a 3.5% reduction in energy consumed. At the lower speed, there was a 6% reduction. So again, improving the voltage wave shape supplied to the drive improved the operation of the drive, lowered the power consumption even further. So then we decided to do a simulation on a smaller generator with the passive filter solution. Now the customer wanted to reduce the size of the generator. They didn't want to go too small because they were too nervous about with all the problems that they had initially with the smaller generator. So we simulated at 350 kilowatts. If we look at that, we can see that there's still very low current distortion and voltage distortion, and so that would meets all of the requirements, all the harmonic requirements. They could have gone to a 200 kilowatt generator and still would have had low current and voltage distortion. But like I said, our customer was too nervous about the fact that they had so many problems before and decided to choose a 350 kilowatt generator instead. So when they were running at the 350, you can see the computer simulations, field measurements, again, voltage and current distortion very closely matched the simulations. There was a substantial reduction in power consumption, and improvements, reduction in K-bars and so on. Again, the improvement in power consumption we believe is due to the fact that the harmonic filter improved the operation of the VFD. So finally, let's look at the actual field measurements and calculations that we did to determine the fuel savings that resulted from the harmonic mitigation. So with a 500 kilowatt generator with a VFD just equipped with an AC line reactor, as we found the situation, it was 137.5 kilowatts. When we added our filter, it dropped to 111 kilowatts. So if you look at the percent loading on the generator, there's 27% loading in the first case and 22% loading. So with the filter, there's a slightly lower loading percentage, which takes it even further down into the less efficient operating range. But because of the reduction in the kilowatts, there was a substantial reduction in the fuel consumption. So it went from 11.8 down to 10.1 gallons per hour, which operating 24 hours a day, 30 days a month, went from 8,500 to 7,200. Based on the cost of fuel at the time of $3.80, we dropped from $32,000 a month to $27.5, a reduction of $4,600. That reduction was enough to pay back the filter in a month and a half. We had a 14% fuel savings, and that reduction in fuel savings now resulted in less emissions in CO2. So we used a calculation of 10.2 kilograms per gallon, which came out of this paper, an IEEE paper. And at that level of emissions, we were running before at 120 kilograms of CO2 per hour, and that dropped to 103. On a monthly level, it dropped from 86,400 to 74,000, a reduction of 12,240. So a substantial reduction in the emissions sent into the environment. Then when we look at the smaller generator, and again the customer decided to go with a 350 kilowatt, even though they could have gone smaller. The power consumption was 117 kilowatts. That was 40% loading, so slightly higher, closer to the optimal efficiency of the generator, which improved the fuel consumption further. So now we're only at 5,000 gallons per month, or $20,000 per month, a savings of $12,000. 38% reduction in fuel consumption. And the emissions now were reduced by 33,000 kilograms of CO2 per month. The generator was easily justified on this reduction in fuel savings, and also the emission reduction proved to be the equivalent of taking 84 automobiles off the streets. So very easy to quantify, excellent fuel savings and emission reductions as a result of the harmonic mitigation. So to wrap up then, if we look at generator applications, consideration must be given to the amount of nonlinear loading, and the harmonic distortion that these loadings will introduce. Rule of thumb sizing from generator manufacturers is to at least double 2 to 2.5 times the generator capacity supplying the load. This leads to much higher installation and operating costs and excessive emissions. Even with oversizing, you can still have voltage distortion levels that can cause operational problems, as we did in this pumping application. But if we apply effective harmonic mitigation, the need to oversize can be eliminated, and therefore we can provide significant fuel and energy savings and lower emissions throughout the life of the installation. So thank you very much. That completes the webinar portion of it. I believe there were probably some questions that were being asked as we went through that seminar, so we'll now go to those questions and I'll try to answer those for you.
Okay, so the first question is the month and a half payback a typical number, or was it only specific to this case?
Good question. I would say it would be reasonably typical. Obviously, one application is going to be different from another, but you're dealing with the same level of harmonics typically. You've got a filter that's going to have the same level of efficiencies. It's going to reduce the harmonic content equivalently. So I think you could expect similar type of reductions, but even if it was slightly longer, still produces excellent paybacks.
Okay, the second question is, what if the generator supplies single-phase loads or phase-to-neutral loads?
Good question. This particular application was a three-phase load, and a three-phase load, nonlinear load, is going to generate 5th, 7th, 11th, and 13th harmonics, as I introduced early on in the webinar. When you're dealing with single-phase phase-to-neutral loads, you'll now have the addition of third harmonic components. These will also load down the generator, also require that the generator be oversized, also increase fuel consumption. It's just a different type of treatment methods that would be used. We do have we would probably use some of our auto transformers or NCE and CNCE to treat the 3rd, 5th, 7th, and 11th harmonics. So the problem is the same, it's just different forms of treatment. The results will be just as good.
Can the MIRIS software, simulation software, make generator sizing recommendation for us?
Yeah, the Solve software that we demonstrated here in the webinar is available to anybody. It can easily be downloaded from our website. It's relatively simple to use and easy to use. It won't make any specific recommendations on generator sizing, but it will calculate the current harmonics and voltage distortion that will result on your generator application. So if you run the simulations, look at the results. If your current distortion levels are substantially reduced down below 10%, like the generator manufacturers say, if it's below 10%, you can only need to oversize by 1.4 times. If you get even lower than that, you can get even closer to one-to-one relationship. But that simulation, then, you can use that simulation to identify that there won't be high harmonic content, and therefore you can go with a much more closely designed capacity for your load.
Is the oversizing just on the component of the load that's nonlinear, or oversizing of the peak estimated load?
Very good question. I believe it's on the total capacity of the generator, and the total load, so the total size of the load. So if you have 25% of nonlinear load and around 25% or higher nonlinear load, and the generator manufacturer then would recommend that you oversize, then you need to look at your total load, and you need to oversize relative to your total load.
I have 4 500 horsepower motors upgraded to all VFDs. Is 2,000 kilowatts required good enough?
So if a 500 horsepower motor is going to be about 400 kilowatts of load. 400 kilowatts is going to be 1,600 kilowatts. If you put proper harmonic mitigation, then a 2,000 kilowatt generator will be fine. If you don't put it, you just put a 3% line reactor, then you're going to need to go with probably about a 5,000 kilowatt generator. So substantially different.
So that leads to our next question. Please explain further about doubling size of the generator feeding nonlinear loads.
Yeah, so I did sort of answer that a couple questions back. What you would need to do, and this is the same person that asked the previous question about the 4 500 horsepower motors. So in that application, if you're only putting, say, a line reactor and no further mitigation than that, that's quite a large. It's quite a bit more than 25% nonlinear load. That's really about 80% nonlinear load. If it was a 2,000 kilowatt generator, so that 2,000 kilowatt generator wouldn't work. So you would need to go at least 2.5 times that load if you weren't putting harmonic mitigation. So as I said earlier, you would require about a 5,000 kilowatt generator in that application.
How to use your filters to reduce harmonic content for the generator that supplies to IT servers as a backup.
Okay, so IT servers, it depends how the servers are connected. Some servers might be connected phase to phase. Other servers might be connected phase to neutral. If they're connected phase to neutral, they're going to introduce 3rd as well as 5th and 7th and 9th harmonics. So there would be a different type of filtration required, different type of equipment that we would recommend in that application. But still can be every bit as effective as the wide spectrum harmonic filters that we use on the variable speed drive applications. So that is something that we could work with you on, follow up with you on, and I'm sure come up with a very effective solution for it.
This is it for our questions.
All right, so I think that is the end. So in closing then, I'd just like to thank all of you once again for joining us. I would encourage you to visit our website. There's on our website in the download section, you can download the IEEE paper on this case study. I will provide more details for you on the analysis that we did. And also our webinar will be posted there, and you will be able to download that webinar and get all of those that information. There'll be notices going out with instructions on